Our next speaker will be
Oh,
Omid Mahmoodi.
change that.
Yeah. Also from the Saskatchewan Geological Survey.
Hello everyone, thanks again for being here for the short course and also for the Saskatchewan Geological Survey open house. Processing and interpreting magnetic data is the second part of this short course, and the main focus of this presentation is processing magnetic data. Airborne magnetic survey is a rapid and inexpensive method to provide continuous coverage of magnetic field measurements. The measurements are direct representation of the physical property of underlying rocks. By processing and interpreting magnetic data, what features can be resolved? It can be stratigraphy, structures, burial depth and 3D orientation of the structures, metamorphism, alteration, mineralization, or magnetic mineral content in a rock. When it comes to discover a deposit, geophysical data can be used as either direct or indirect targeting techniques. A deposit can be directly targeted when magnetic signature is associated with a deposit, for example, kimberlite or banded iron formation deposits. But on the other hand, in indirect targeting, favorable host rocks, structures, or alteration zones are the targets. Using magnetic data for direct targeting uranium deposits is generally ineffective, but it is highly effective for indirect targeting. First step is to obtain your data set based on the scale of your work or expected output of your project. There are plenty of geophysical data available to the public in Saskatchewan Geological Survey assessment files with different scales, different resolution. Second step is to obtain complementary information such as geological map, historic reports, and geophysical data, topography, or satellite imagery. These data can help you to interpret the data. Then data are processed, magnetic data are processed and compiled in ArcGIS or any GIS platform. We have processed maps, structural framework, faults, magnetic domains. All this information can be extracted from the data. Then they can be integrated with complementary information, and it results in integrated interpretation map. Just a few basic information about the magnetic field, Earth magnetic field as you're working with magnetic data. The Earth magnetic field is a vector. Its direction can be described by inclination and declination degrees. Inclination degree is the degree between the magnetic vector and horizontal. And declination degree is a degree between magnetic slope and geographic north. The magnitude of the vector is described as magnetic intensity, and it's usually reported in nanotesla. Each observation of the Earth magnetic field has three components. First, 97 to 99% of the Earth magnetic field is generated within the outer liquid core with core magnetic source. These components should be removed from the data when we are processing the data by IGRF correction. 1 to 2% of the magnetic field is external field with solar magnetic source. These components should also be removed from the data by diurnal correction. The only component that we are interested in is crustal field, which is 1 to 2% of the Earth magnetic field with cross cross-salt magnetic source. The cross-salt magnetic field can be induced magnetic field or remnant magnetic field. Induced magnetic field is produced when Earth magnetic field H is applied to a magnetizable body here, and the body then acquires magnetization. The induced magnetic field is always parallel to the Earth magnetic field, and its amplitude is proportional to the Earth magnetic field, that location at that time, and magnetic susceptibility of the materials. Permanent magnetization of materials is impossible above a temperature which is called Curie temperature. When magnetic materials cool below the Curie temperature, the domains within magnetic minerals take an orientation parallel to the Earth magnetic field or any external magnetic field present at that time. These magnetic minerals keep this magnetization, which is called remnant magnetism. However, the Earth magnetic field can change over the time. Remnant magnetization can be parallel, or it can parallel to the Earth magnetic field, or it can have different direction. That's the reason why we can see a strong negative magnetic anomaly for magnetic body. Magnetite, pyrrhotite, illmenites are the most important magnetic minerals. Generally, mafic rocks have higher magnetic susceptibility than felsic rocks. The same way you can see sedimentary rocks are relatively low mag rocks. You can see there is a significant range of variation in magnetic susceptibility of the rocks, and it can become even more complex when we see that some events such as alteration, mineralization, metamorphism can change the magnetic content of the rocks. So understanding the magnetic susceptibility of the rocks is a key to interpret the data. Any processing work on the magnetic data starts with preprocessing. Diurnal correction is applied to the data to remove the effect of change in the Earth magnetic field during the time of the survey. Diurnal correction can be some values between 20 to 80 nanotesla. The Earth regional magnetic field, as I said before, should be removed from the data by IGRF correction. IGRF stands for International Geomagnetic Reference Field. Leveling error are these long wavelength features parallel to the survey lines. These features should be removed from the data. They are mainly caused by the change of the position of magnetometer. Tie lines, which are flown perpendicular to the survey lines, are used to remove the data. Any remaining long wavelength feature parallel to the survey lines then are removed by micro leveling. Then the data are ready for grading. As you can see, you can see leveling error here, and they are removed in these grades. There are different algorithms to grade the data. Minimum curvature and bidirectional algorithms are most common techniques to grade the data. Here is an example of a magnetic survey flown in the flip-flown area with 200 meter line spacing. The data were graded with different grid cell size. As you can see, by increasing the grid cell size, we're losing the details in the grid. And by 400 meter grid cell size, we get smooth grid. It's recommended, the grid cell size is recommended to be half to a quarter of the line spacing. We have 200 meter line spacing, so the ideal is 50 meter, which is a quarter of the line spacing. It's always helpful, as Colin mentioned, to visualize your data with different color scales and different ways. This is the gridded data visualized by a normal distribution color scale. Details are enhanced in the color shaded image. You can see more details in this grid. The same grid, the same data are visualized by linear distribution color scale. In this map you can see very high magnetic zones. The same map with grayscale, some people prefer to visualize their data with grayscale. It can be helpful for edge detection when you're looking at your data to extract the edges. Filters are applied to enhance certain components of the data and suppress noise. All filters that will be discussed in this presentation can be categorized in residual, regional separation, source edge detection, and source depth estimation. We will see in the next few slides what they do and when we should use these filters. First, reduction to the pole. It recalculates the data as they are collected at the magnetic pole. So it removes the effect of the geomagnetic field inclination and declination. RTP map is a simplified magnetic map as the magnetic anomalies are located above the magnetic source. We have inclination and declination here, and this map is the RTP map. It was recalculated as it was the data collected at the magnetic pole. We don't have any effect of inclination and declination here. And you can see these magnetic anomalies are located above these magnetic sources. So it's easier to interpret the map. High and low pass filters are based on the fact that high frequency information with short wavelength are related to shallow sources, and long wavelength, low frequency information are related to deep sources. When magnetic fields are collected along the survey lines, the measurements are a combination of low and high frequency information. The geophysical signal can be geophysical data can be divided into different frequencies, and then the filters can be applied on those data. High pass filters is applied to the data to reject low frequency information related to deep sources, so we have shallow sources enhanced in this map. On the other hand, we have low pass filters. Low pass filters reject high frequency information. It removes the details and shallow sources from the data, and we get a better understanding of the magnetic source at depth. Automatic gain control. It recalculates the data set to normalize the amplitude of the magnetic anomalies. Usually what we have in the original data, subtle features with small amplitude, they are masked by high amplitude anomalies. So what it does, it normalizes the amplitude, it normalizes the data, so we have the same amplitude for both strong anomalies and subtle anomalies. Here we can see subtle features which are usually masked in the original map. Upward and downward continuation simulates field at higher or lower elevation. Upward continuation, for example, this map is 500 meter upward continuum. It removes or minimizes the effect of shallow sources and noise in degrees. On the other hand, downward continuation, it enhances the response from sources at shallow depth by basically bringing the measurement plane closer to the surface. When the measurements plane get closer to the surface, we get stronger response from shallow sources. But you need to be careful about downward continuation because it gets too noisy when you do the downward continuation. Analytic signal, it simplifies the magnetic map by putting magnetic anomalies over the source edges. So it's easier to look at the analytic signal to locate your magnetic sources. Vertical derivative, first or second order. What it does, it removes the effect of deeper sources. So we have high frequency formation enhanced in this map. It's useful to look at the first vertical derivative for source edge detection and locate the shallow sources anomalies. Directional filters is an example of match filters. Directional filters pass or reject signal in a certain direction. For example, this original data, we have strong north-east linear feature here. It can be structures, or it can be a dike signal in the magnetic data, or even it can be leveling error in your data if you want to reject those errors in your data. After applying directional filters, 45-degree azimuth, it rejects all these linear features. On the other hand, in these pass filters, it enhances the linear feature with 45-degree azimuth. Source edge detection methods has a series of techniques to enhance the edge, the source edge in your data. The source edge can be magnetic domain borders, can be edge of structures, faults, or dikes in your data. Let's start with RTP, reduced to the pole map as original data. Total horizontal derivative map emphasizes source edges by putting maximum, by having maximum value at a contact. So all these high values here, they represent the contact or source edges. Theta map has its maximum value equals to 1 at a contact. Tilt derivative has 0 value over contact. It's positive over strongly magnetized body and negative over weakly magnetized body. The main difference between tilt and theta map is the fact that tilt derivative emphasize or enhance more deep sources, but theta map is useful for both deep and shallow sources. You can see more details in this map. On TDX derivative map, you can see the sharpest contacts in your data as 0 values are bracketed by positive and negative values over the contact. All of these maps can be used for edge detection. Multi-scale worms is a technique to extract edges at various continuation levels. This is an example of the magnetic survey in the Athabasca Basin. This multi-scale worm analysis was undertaken by Flip from Geological Survey, South Australia. What this technique does, first it upward continues the data at different levels and extract the edges at different levels. So you can see edges, for example, for the magnetic data 500 meter upward continued. You can see details in this map. Then edges are extracted from 5 kilometers upward continued data, 10 kilometers upward continued data. As we go higher, we can see major magnetic domain at depth. 20 kilometers upward continued, the edges are represented by thick red lines. 30 kilometers, and at the end you have this map. You have the source edges, the edge of deep sources as well as shallow sources, so you can turn off or turn on specific levels to do your geological modeling. After you have the produced, processed map, all of those maps can be compiled in a GIS platform, and the lineaments can be drawn manually. For example, here we have magnetic total field map, field derivative map, and TDX derivative map. The lineaments are manually drawn over the edges, over the troughs or peaks. When we have the resultant interpreted lineaments map, it's time to integrate those information with other complementary information such as geological map or interpreted maps from different geological, geophysical data. And at the end we have the final integrated map. Two techniques: source primary imaging, which is available in Geophysics software, and also Euler deconvolution are two techniques to estimate the depth to top of your magnetic sources. Both of these techniques estimates the depth based on the first amplitude of the magnetic anomaly and also the gradients, the rate of change of your magnetic data. You have the edges extracted from the data in previous processing techniques, and you can estimate the depth to top of those sources. Then you can use this information to have a 3D geophysical model. Just a quick mention, if you want to have the distribution of magnetic susceptibility in a 3D space, you need to do the inversion. When we have the observed data, data can be inverted to obtain the magnetic susceptibility model, which can reproduce the observed magnetic data. Of course, if we don't have any geological information or physical property measurements to constrain this inversion, we get a smooth model. But we can constrain this model with the geological information that we have from variable information or some measurements at the surface to constrain this model to be consistent with geophysical data and also with the geological information that we have. What are the key magnetic signatures of unconformity uranium deposits? You're familiar with this model for unconformity uranium deposits. As I mentioned before, using magnetic data for direct targeting is not possible. You don't have any magnetic signature associated with the deposit. But what are the other factors that can be detected by magnetic data? We have the alteration zone, which is usually associated with low mag zone. We have these structures. The structures can be extracted from magnetic data when it breaks on the magnetic features. And also host rocks, which are which is normally platic with the sedimentary rocks, and they're usually associated with mag-low zone, the Athabasca Basin. But these features are most often, but not always, true for all the deposits in the basin. A couple of examples of uranium deposits in the basin and a magnetic signature associated with those deposits. Magnetic map of the southeastern margin of the basin. Rabbit Lake is located here. We have MacArthur River here. Cigar Lake is located here. All these uranium occurrences are in the low mag zone. The low mag zone can be alteration zone or platic with the sedimentary rocks. Both of those features are associated with low mag zone. And also they are along these lineament features. It can be big structures in the basin. Another example of a Shea Creek area. Most of exploration activities are concentrated in this low mag corridor here. Again, can be structures, alteration zone, or platic sedimentary rocks. One more example, Fear Island at northeast of the basin. Again, this low mag corridor is the main focus for exploration works in the area. More uranium project. This is located here. Again, most of these uranium occurrences and exploration activities are along this low mag corridor here. Along the structure that we zoom in, you can see this low mag zone. There are several software that you can use to process your magnetic data. Geosoft is the most common software for processing magnetic data. USGS, Geosoft executables. These are free extensions to the Geosoft. You can download these from USGS website and use these extensions to process the magnetic data. PA Discover, GoCat with its VPNG package to process magnetic data. Income, mainly for your modeling. UVCman 3D for the inversion. ArcGIS for compiling your data and interpreting the data. There are free viewers if you want to share your results with your colleagues. Geoscience Analyst, Discover Viewer, and Geosoft, all of them have free viewer. Important websites for downloading geophysical data. Plenty of magnetic data are available to the public to download on Natural Resource Canada website. And also assessment files available on GeoAtlas, Saskatchewan Geological Survey. Thank you.
Are there any questions? Claire?
Omid, you said that the potential for alterations to be mag-lows in the sandstone. Could you elaborate on that? What's causing that?
Hydrothermal alteration is normally associated with the magnetization. So magnetite is consumed by alteration and minerals. It's transformed to non-magnetic minerals, so it reduces the magnetic intensity of the rocks.
Were you asking about the sandstone specifically? Did you say in the sandstone? Did you mean to say that?
No, it's a basement. Because sedimentary rocks, they have low magnetic
The one image of was from partly confused because it had the alteration zone well out into the sandstone, and that's we're talking about the sandstone. So you're referring to the basin only?
Yes, basically.
This is a bit of a follow-up question. Go ahead, Dave.
Well, I have a long list of questions. I know we don't have time for it. So I'll just focus on the first one. Magnetic remnants in the Athabasca Basin. How common is it? And how do we recognize mag remnants from just our current magnetic field? And how do we get rid of it? How do we recognize it and deal with it?
Remnant magnetization should be, for understanding remnant magnetization, that we should take some samples, send them to the laboratory to measure the remnant magnetization, if there is any remnant magnetization associated with the rocks or not. Actually, we keep samples for remnant magnetization.
Randy Enkin's done a bunch of work in the eastern Athabasca, I don't know how long ago, and they did find a lot of remnants in the hematite of the rocks. But yeah, so there's a lot, but it doesn't really impact it because it's non-magnetic for all intents and purposes to begin with. So it's not like you're seeing the anomalies where it should be a point anomaly and you'd have the anomaly in the south or the north or off to the side. Because, so for the RTP, what Omid was showing, if you had remnants, you wouldn't have a point anomaly. You would have it would look like a dipping body essentially.
So there's some, actually, I was in a meeting once at Ariba, and they were talking about some of the Archean domes, and the cores of those domes are, in some cases, maglos, and they're typically interpreted as sort of a saddle of metasedimentary rocks. And this particular guy said, no, that's remnants. Basically, that was, so the outside edges of this dome are being heated during metamorphism to above the Curie temperature, but that the core is being shielded somehow. So it's not being reworked, I don't think. And so some of the middles of the domes are lows, and that's remnants.
So, yeah, well, we can't assume that.
Yeah.
You told us that. We can't assume
That was the interpretation of the
Because
geophysics.
our problem is we drill Archean granites.
Yeah.
Sometimes in our sea of metasedimentary blue, we're hitting granites,
Yeah.
Archean granites in there. They're not showing up.
Right.
So it's remnants is the explanation. I'm just wondering if there's any way to see through that sea of blue, knowing that there's different pathologies.
You could sample it, and so Randy Enkin has a laboratory at the GeoC Pacific, and he does remnants measurements. And I'm not sure, Ken, do you know of any other laboratories? I think there's a guy in London who's doing it now, London Western University. So it'd be good if you were interested to find out if there is a remnants magnetization associated with the rocks to ship it off and get tested.
On the processing front, the quick fix is you can run an analytic signal and just convert everything from negatives to positives, or Geosoft now has their magnetic vector program to give you some insight into the presence of remnants. It's a processing solution as opposed to a direct measurement. You end up, there's other, parametric modeling can allow you to, see whether the geometry in a parametric model actually makes sense for induced response. And if it's not, it could be remnants in that case. I mean, the sampling story is, if it were all on the outside of the basin, it'd be relatively straightforward.
Yeah.
We're talking here, maybe these samples may be very, very expensive and going the Loomis truck when they're taking them to wherever they're going.
Yeah.
So you may have to kind of come up with indirect means to get some. But it probably should be datable from the point of view of, if you had a better geochronology of the basin, you know what places would be likely to host remnants.
Yeah.
And that might be a task that at some point the local survey could help with and say, we know these rocks at particular ages have a propensity to have real remnants as opposed to alterations.
Just add to that, Ken, one of the key giveaways that's not always guaranteed, but if you're concerned about it, when you try running your inversions, as a first pass, you get some particular areas that really don't want to fit. That's a good indication that there might be remnants there. And so you'll get big negative loads that the inversion just can't fit, particularly in VPMG. That's a good indication that there might be remnants.
There is an instrumental approach which has been in beta testing, I guess. It's a squid magnetometer that Anglo developed. And by measuring the vector components very accurately with the squid, they can actually infer remnants being present in a way that normal total field or even conventional gradient surveys, good as they are, they don't have the resolution the squid has. And there was a picture in ETD, it looked like a big thermos about 2 meters high, and it was actually towed behind a small fixed-wing aircraft. And I know the system works. NCOM has worked for, Tensor has worked with them on this, but it's not been commercialized. So there is an observational thing remotely, not on samples itself, but that you would actually fly in like a conventional airborne survey, but it hasn't found a home yet in the commercial world.
Or Don, did you?
I did. Basically, it follows up Claire's comment. You mentioned that the alteration shows a magnetic glow and the post-rock also shows a magnetic glow. Is there a way, do you know if there's any discernible differences in those lows that we can contrast? So you can actually see the alteration in those rocks?
The low mag for the sedimentary rocks is more extensive, and mag low associated with the alteration zone, which is restricted to the vicinity structures in the area.
Right, but is there an actual measurement that you can say, if you're looking for those alteration zones in the post-rock, that you could use that to contrast, so you know you have a value that you could use as, this is my alteration, or even a relative difference that you could use to contrast them so that you could then see the alteration and then magnetic glow.
Yeah, it was the thing that Colin was talking about when we have both protodic, the sedimentary rocks, and alteration both have low mag and magnetic susceptibility. So it can be alteration or it can be
you got a range of responses that both rocks can have.
Right, I guess what I'm getting at is if we could find that feature, that you could double up, basically say alteration will have this mag low plus, or there's a specific contrast between the mag lows of a P-light versus the mag lows of an alteration zone, we could use that to help factor in further.
I think you need to integrate other data into it.
Probably.
Mineralogy and geochemistry.
also magnetic
With
susceptibility.
the magnetic susceptibility measurements, yeah.
The dynamic range is going to be so small that,
Yeah.
Yes.
particularly considering how far away you are measuring, like if you're
Yeah.
at 500 meters of sandstone, there's no way you can get this.
Yeah, I
That's
agree.
important to know as well.
Yeah. So I think this is where the integration of different data sets becomes much more powerful. You need all these different types of data to interpret what that anomaly means.
Sure. Okay, thanks.
One more quick question, yeah, Kathy?
Just the burning technique. You showed the example where you were imaging quite a depth. Can you pretty much customize the burning technique to get, to acquire information from shallow depths, etc.?
Yes.
Okay.
Yeah, because when you, for multi-scale worm technique, you acquire continuity your data at different levels. If you want to get the shallow sources, you acquire continuity your data 200 meter, 500 meter. You can see more details in your data.